Welcome to the third lecture of the reaction kinetics series. Today we're going to look at the theories behind reaction kinetics. So just a quick recap, we have done all this in gray and now we are at a part where we really look at the theories behind all this. Um, the theories are actually a microscopic description of the reaction, explaining why changing physical factors are going to result in a change in the rates. And the two theories that we'll be looking at today will be collision theory as well as transition state theory. So let's begin with collision theory. We are actually very familiar with collision theory as we have been earlier exposed to it. It states that reactant particles must collide before they can react, and only one collision in every 10 to the power 14 collision leads to a reaction. So but also the fact that your reactant particles is always in random motion, so it does proceed quite well. Reaction will occur only if particles fulfill the two requirements we have over here. Number one, the colliding particle must possess the minimum amount of kinetic energy, called the activation energy, for the reaction to proceed. And number two, they must be colliding in the appropriate geometry, if not orientation. So it is 1 in 10 to the power 10 to the power 14 collision that is in the right orientation, plus that both of them, the particles actually contain the kinetic energy that is required for the reaction to proceed, because the minimum requirement is actually your activation energy. So such a collision will lead to having an effective collision. So collision and effective collision is quite different. Now, if we look at our Maxwell-Boltzmann curve, where the natural distribution of particles of different energy is being charted at temperature T, then we will be able to picture the fact that the activation energy is like a minimum requirement. So activation energy will dictate who actually possess the amount of energy to proceed with the reaction. And so this is the group of the particles that is able to proceed. The one in white or not shaded area are the ones that do not possess sufficient energy to proceed with the reaction, even if they happen to be in the correct geometry as they collide with each other. Okay, so this area indicates the number of particles that has energy of at least activation energy. So what are we talking about when we use the term geometry orientation? Collision with inappropriate geometry will end up being an ineffective collision. So like this, there's no product form. So this is not the way that is considered appropriate geometry. There's one way where they meet, and that's the correct one. So collision with appropriate geometry, but insufficient energy in the colliding particle, you will also end up with ineffective collision. So they collide correctly, but because not enough energy, that's why very slow in their animation. So if your collision is with appropriate geometry and sufficient energy, resulting in an effective collision, this is how it will look like. Hey, and then you have your product form. So this is the difference here. We have the two requirements and we need to fulfill both of them. The rate of reaction is directly proportional to number of collision per seconds between the reacting particles involved in the rate determining step. Now, focus on the fact that it is not random particles, not all the reacting particles, but only the particles that is involved in the rate determining step, and of course, following the coefficient in that particular step. Now, the fraction of this collision with the correct orientation are and the fraction of this collision with sufficient energy to overcome the activation energy of the reaction are with these two requirements being are accounted for, then they will proceed with the reaction. So let's look at the transition state theory. Reacting particles with energy more or equals to activation energy come together in appropriate orientation to form a transition state or activated complex. And this transition state either decomposes back to the reactant or rearranges itself to form the product. So it's at a point where it could go back to its reactant form or form the products. In a single step reaction mechanism, assuming, the example I give you, the exothermic reaction, it will actually look like this in the energy profile diagram. The enthalpy change can be found between from the reactant level to the product level, in this case exothermic. Transition state is the peak of the energy profile diagram. So transition state or activated complex can be denoted using the symbol that I'm showing on the right, like a two horizontal line with a stroke through it. Existence of the transition state is theoretical. Now, unlike an intermediate can be isolated and we can study them, but transition state is not. It is theoretical. In a way, you can say that the chemists imagine them. We have no proof. But based on the intermediate or the product that we get and the reactant that we start with, we propose that is what happened in between, but we have not much of a solid proof to ascertain that it actually exists that way. So research is still on the way. We can still find more ways to look closer into what happened at that time. So this is our transition state energy level, and activation energy is measured from the reactant to the transition state. Now, I have a EAB labeled on my diagram here, really because should the reaction be reversible, that means the backward reaction will be going from the product to the reactant, and therefore I have the activation energy for the backward reaction labeled as well. Activation energy is the energy gap between the transition state and reactants. For single-step reaction mechanism, where it is an endothermic reaction, the energy profile diagram looks like this. Transition state remains as the peak of the energy profile diagram, and so the activation energy for the forward reaction will be measured from reactant to the transition state level, whereas the activation energy from the backward reaction will be denoted by this arrow over here. Take some time to appreciate and understand why the two activation energy for forward and backward reaction can be labeled as such. Now, this is provided if the reaction is indeed reversible. If the reaction is not reversible, then we will not have a forward activation energy and a backward activation energy. So in the diagram, in this particular example where I have the energy profile diagram of the reaction between hydrogen and iodine gas forming Hi gas, it will look like this. Now take note from the reactant level where I have H2 and I2 added together. The solid line actually denotes the covalent bond, but there will be orientation between the H and I. As they begin to interact, we get to the transition state where the bonds between H and H is partially broken, the bond between I and I atom is partially broken, and the Hi bond is partially formed. As we proceed with the reaction, and the new bonds are being formed between H and I, and they are having interaction between the molecule, no doubt, but the actual covalent bond is between H and I. So this is how it looks like. Your activation energy is measured from the reactant level to the transition state level. Reactant particles need to collide with the correct orientation so that they minimize steric repulsion. Where the reactant particle possess sufficient energy to start breaking the old bonds and forming new bonds during the transition state. So the bonds are partially broken and new bonds are partially formed. The old bonds are now broken at the product stage, and the new bonds are all formed right now at the final stage. Activation energy is a key term that we all must know what it means. It is the minimum amount of energy reacting particles must possess before a reaction could proceed. To get to the transition state, energy is required to, number one, weaken the bonds that is in the reactant particles. Number two, overcome the steric repulsion between reactant particles so that they can approach each other. And number three will be orientate reactant particles to achieve the correct geometry to react. So that is why there is a minimum amount of energy required. What is our understanding of activation energy? Reactions with low activation energy proceed quickly. Well, when you have low activation energy, it means majority of the particles actually possess the required energy. So the moment they have a collision with the correct geometry, they can immediately proceed with the reaction. That's why the rate of reaction will proceed fast. You have a way larger proportion of the reacting particles that have enough energy to overcome the energy barrier. On the other hand, if you have a reaction with high activation energy, then it naturally will proceed very slowly. Because when activation energy is exceedingly high, rate of reaction becomes so low they may not even occur, even if it is thermodynamically favorable.